Okay, so welcome back to this afternoon session. And yeah, so this session first speaker will be Amaresh Jaiswal. He's from IISER, Bhubaneswar, and he is a leading expert on heavy quark polarization in magnetic field and spin hydrodynamics. So it will be a good opportunity for you to listen his talk and ask questions. Thank you. Thank you, Amaresh.
Thank you, Nihar. Good afternoon, everyone. So I'll be going in a little different direction. So till now, in the context of heavy quarks, you have come across phenomena like drag and diffusion, which essentially deals with momentum of heavy quarks, energy and momentum, energy loss, momentum diffusion, and so on. What I will be presenting is now similar physics, but in the context of angular momentum. Okay, so let's start with that. So this, so I'll be talking about heavy quark, and essentially the polarization is very intricately related with the magnetic field generated in heavy-ion collision. And since I checked that I have a little bit extra time, I put in some other application of magnetic field as well. So I have extended my talk. So let me start with textbook Biot-Savart law, moving charges generate magnetic field. This is something which we learn in school. And this is what we expect, that in heavy-ion collisions, since the charged spectators are moving almost at the speed of light, there is very strong but transient magnetic field. Okay, and and actually we expect, I mean, we know that there is a very strong magnetic field. It has to be there, yeah. But a very clean signature of magnetic field is still, not cleanly observed, I would say. Okay, so what I would present here is one such signature of magnetic field, a very clean one at that. Okay, so the magnetic field, when you start dealing with in relativistic fashion, then there is electric and magnetic fields are not independent. It depends on which frame you are looking at, and the field that is produced in heavy-ion collision is huge. So these are very standard things. We all know this. But what is interesting is this 14 Tesla, which is, although it is transient, but it is extremely strong magnetic field. Okay. So and one can actually look at how the magnetic field, the time evolution of magnetic field, how it depends on whether there is the medium is conducting or not. But nevertheless, if you look at very early times, the decay of magnetic field is almost common. And we will be interested only in this time regime where all the models predict similar decay of magnetic field as a function of time. Okay.
How did this, what model was used to model the temperature versus time?
Where? Temperature versus time? Oh, so this is, for example, here, this is static, it doesn't evolve, but this is Bjorken and Gubser models. So right, so it says, yeah, there is lattice QCD calculation for, but then that would be temperature dependent, is what you're saying. But so then that evolution is either, static means probably the temperature is fixed, but here this is Bjorken evolving or Gubser evolving medium, the temperature decreases accordingly. Okay. So let's look at heavy quark polarization in heavy-ion collision. So heavy quarks are produced at early times, yeah, and this has been recognized in measuring the transport properties of QGP. It has been an excellent probe. Many of us are here who have been working on this. That's why we are also here. So, and they are generated in initial hard scattering of partons. So they are produced at early times, and the magnetic field is there at early times. Okay, it decays, but if there is some effect, we better look at probes which are present at early times. Okay. So strong transient magnetic field, and therefore what we proposed is that we should look at it as an observable signal of initial magnetic field. Okay, so the magnetic field can affect a heavy quark in two ways. So first is, a charged particle moving in magnetic field. It's simply, the trajectory is changed, and you can look at it in flow observables. Okay, and people have looked at it, and in V1, for example, and there is some signal, not very conclusive, but there is some signal of magnetic field in V1 But then there's other effect of magnetic field on a charged particle. If it is particles with intrinsic spin and charge, then they are particles with magnetic moment. Okay, and if you have a strong magnetic moment, they will align. The system will try to decrease its, go to the more stable configuration, and it will interact, and the magnetic moment, and therefore the spins will align. So this is, and so once that happens, so initially we have unaligned spins of heavy quark, but in presence of magnetic field, these are aligned. Okay, and then the heavy quark propagates through QGP. Yeah, I mean, it's produced. Of course, this picture is quite simplistic in the sense that heavy quark is produced, via some distribution in the so depending on this, initial hard scattering. So binary collisions, you can kind of sample it inside the QG, but nevertheless, it propagates through the fireball. Okay, and the physics is very simple. So you have spin aligned ensemble of heavy quarks moving through QGP, and interacting randomly with the constituents of the medium. Okay, and each interaction will tend to misalign its spin or make unpolarize the heavy quarks, each interaction randomly based on some time scale or some cross section of interaction. Okay, so the longer it stays in the medium, the more it gets depolarized. Okay, so if you have faster heavy quark, it escapes the medium, it is more polarized. If you have slower ones, it is less polarized. And this is what was observed in experiment by Alice, D star plus polarization. And we predicted that. So the blue curve that we said that, okay, with PT, the polarization should increase. And because the high PT particles are fast, so they stay for lesser time in the medium and therefore more polarized. Okay, one thing to notice is that the magnitude of polarization is huge. If you compare this with lambda polarization in heavy ion collision, okay, this is especially at Alice energies, it is almost consistent with 0. Whereas this one here is extremely high. Yeah? 0.33 is unpolarized, because I will tell you why it's for mesons 1/3 is unpolarized. But look at these values. These values are huge. Okay, so for lambda particles, we know that. Yes, Japa, you want to ask something?
This is unpolarized, right?
Which one? Here.
Yes, at small PT. So as you increase PT, you get more polarization? Is that
yes,
the way?
Yes, this is consistent with the fact that if the heavy quarks are polarized in the magnetic field, then high PT ones are faster, they escape the medium quicker, and they get less depolarized. So you have more polarized heavy quarks. So I will also show the mathematical calculation. I will come to that. But the physics is very simple in that sense. Okay. Right. Right. So and the other thing that I was trying to say is that if I try to attribute the mechanism which polarizes light quarks like lambda, the same mechanism doesn't work here, because for lambda we have very small polarization. So the medium polarization is not playing the main role here. It's the initial magnetic field. That's what our claim is. I will tell you why. Also, it will be. It cannot be the medium polarization. Okay. So let's go into a little bit of mathematics. So first, okay. So the idea is that this is prediction for baryons. So for mesons, the polarization depends on average of cos square theta, whereas for baryons it depends on average of cos theta. There is a mod, because the prediction is, so this is prediction for baryons like lambda c, for example, and there is mod. So anti lambda c would have negative polarization. That's the prediction. Okay, but the blue one is with the data that we fit, and with the same parameters we give prediction for lambda c for baryons. Okay, so let's go into, yes. Yes, Peter.
Yeah, go back. You're right. So looking at the data, in fact, the first 3 points are consistent with
0.
0. The fourth point from the left, maybe a 1 sigma effect. So rather small. The only truly significant point is the rightmost,
Right.
which is extremely high PT. There's a distribution clearly, let's call it on average 20 GeVs. There's a 20 GeV baryon.
Right.
So-
Meson, this term. Yeah.
Sorry?
This term meson.
Meson, okay, 20 GeV
Meson.
term, the meson.
Yeah.
Comes from a charm quark that's got some good fraction of that because of fragmentation function. This is basically a charm jet.
Right.
So basically you're measuring charm jet polarization.
Okay.
So how does that happen? I mean, jets are formed very quickly and then there's a shower and it's not just a charm quark. It radiates gluons. There's additional
Right.
hadronization effects, which can dilute it seems like an immensely complex process. So what this is measuring is the polarization of jets. Now, it's known that even in unpolarized collisions, there's lambda polarization within jets, which has nothing in proton-proton collisions, which has nothing whatsoever to do with medium. So is there some connection to the understanding of lambda polarization within jets and what we're observing here that's got nothing to do with
Medium.
with the medium? Has this been measured in, so it doesn't actually specify, my name is probably on this paper, but I didn't pay attention. This is in heavy ion collisions?
Yes.
Has this been also measured in proton-proton collisions?
I haven't talked. I don't know. I don't think
This
so.
would be a crucial measurement to distinguish other QCD mechanisms that can polarize particles within jets
Right.
just by other QCD mechanisms versus a medium-induced polarization.
But this is not medium. I never claimed this is medium.
Huh?
So my claim is that this magnetic field, this is early magnetic field, which is polarizing it.
Good. Not even, sorry,
Not
not even a
even the medium.
medium, a nuclear collision. You also see such polarization of proton-proton collisions because such polarization has been observed with lambdas as well.
Okay. I don't think there are measurements for proton-proton collisions.
This is a crucial check.
Yeah, I think so. Yeah. Okay. So our formalism will be based on we'll be working in the heavy quark rest frame. So we have to translate the magnetic field to the heavy quark rest frame. So we have to Lorentz transform it, and it is a transformation for the electric and magnetic field to the heavy quark rest frame. Okay. However, what we can do is we can just doing an average over ensemble of heavy quarks. You can see that on an average, the magnetic field experienced by the heavy quark is along the magnetic field in the lab frame. Okay, so essentially, even if the heavy quarks are polarized with some angle with respect to the magnetic field in the lab frame, on an average, the angular distribution would expect to cancel at linear order, and you will only see polarization along the magnetic field observed in the lab frame. Okay, so that is one thing to notice. And then what we do is we start with this so-called Langevin equation, but with spin, with magnetic moment or spin. Yeah. So this problem was actually first studied by Debye. So he considered electric dipoles in an electric field, okay, and see how it got depolarized in a medium. Okay. So similar physics we are extending to magnetic dipoles. So the equation is this Landau-Lipschitz Gilbert equation with a stochastic noise term, which we consider white noise. That has already been explained to you what a white noise is. Just we worry about correlations of noise, and only the quadratic correlations survive. I think Santosh has already discussed that in detail. Okay, so right, so we have these are the magnetic fields, but since we are dealing with spin, so essentially what we do is we define magnetic moment in terms of spin, particle spin, with this gyromagnetic ratio gamma. So in terms of that, in terms of spin, we write down the whole equation. There is a stochastic term here. We do not consider a stochastic term in the second term. In principle, one could, yeah, but we have a Fokker-Planck description, and we can show that this stochastic term is cubic order. So using this, fluctuation dissipation relation, you can show that this appears at cubic order in dissipation. So we ignored it essentially. Yeah. So we only keep this one, which is linear order in diffusion or drag of an angular momentum. So this is subleading. So we basically ignore the noise here. Okay. So lambda is the damping coefficient. So I will tell you what this. So this term is the precession term, and this is the one which essentially drags the spin back to. So the idea is that you have S cross B, which is essentially the precession term around the magnetic field, and then this is the term which is trying to drag the spin back to the orientation along magnetic field with the damping coefficient lambda. This is how we explain it, and then in a generalized form you can write it like so. So this Langevin equation can be written in a most general form like this, which is lambdas.
The lambda and psi, they satisfy some kind of fluctuation dissipation theorem?
Yes. So actually, that's a very good question. So we don't know such a relation yet. So that one has to obtain such a relation by appealing to the fact that when you go to the equilibrium, how do they behave, and that this actually we are working on. But if I were to just look at dimensional analysis, just look at dimensions of lambda and psi correlate will bring a diffusion coefficient. So lambda and d, for example, here. So thus the dimension analysis tells us that d will be equal to lambda t. At least this works in the conformal limit where the temperature is the only scale in the picture. Then d equal to lambda t is at least d proportional to lambda t is good enough. But it turns out that the way we are going to solve it, we will not need lambda at all. It won't come into the picture with the assumptions that we make. So let me go ahead and explain. Okay. So we have this generalized Langevin equation, and this with these choices of A and C, you can actually put it back into what we had for Landau-Lipschitz Gilbert. So this is essentially writing in this form, okay, where in the components form essentially, where we assume statistical properties of white noise. So the mean is 0, and we have this variance, okay, and d is a diffusion coefficient similar to what we have when we have when you deal with momenta, okay, and then with this actually one can ask the question about probability. So you have ensemble of heavy quarks, okay, evolving, and then when you ask the question that what is the probability that the spin of a heavy quark lies in this particular range, okay, this is a classical treatment, by the way, okay, so I'll be treating spin classically. Okay, so this is some just a declaration in the very beginning that we are going to treat spin classically. So the idea is that the whole of, although this is spin half particle, the whole of Bloch sphere is allowed, and then as long as it satisfies some normalization conditions. Okay. So then we ask the question that what is the probability that the spin of the particle lies in a certain lies in a certain angular range. Okay. So that gives us the Fokker-Planck equation, and it can be obtained by a very well-known so-called Kramer-Small expansion, which is nothing but Taylor expansion. Okay, so one can do this, and then this is for individual heavy quark, and this is for the probabilistic picture. Okay, so from Langevin to Fokker-Planck, you can arrive via Kramer-Small expansion.
Yeah. So here you're ignoring the spin orbit couplings, right?
Yes.
There's no coupling to the momenta or anything.
At this point of time, no. There is no coupling to the momenta. Yeah.
So this is fine if you are a very non-relativistic particle. But
okay.
I'm trying to understand if it is some very high PT thing coming out. Is that a justifiable assumption for that?
Right. Okay. So in here, if I were to have the spin orbit coupling, it would enter in.
For example, there'll be a Thomas precision.
Right. So in the precision
term. This will all be relativistic, suppressed for a non-relativistic particle.
Yes. So for a relativistic particle, I understand the one should take.
Yeah, BMT equation. Yeah, there's a BMT equation.
Yeah. So I have checked that this BMT equation one can in the okay. So to answer the question, we're working in the Heavy-Quark rest frame.
In the
Heavy-Quark rest frame.
Heavy-Quark rest frame.
So then this Bargmann-Telgeti Michel equation, BMT equation. So we in the Heavy-Quark rest frame, this equation reduces to BMT.
So then to kind of match with the kind of data you're saying, you would boost it at the end? You
so
would boost the final predictions at the end? Is that the point?
So the idea is that one should boost the observable to the lab frame. Yeah, this should be the case ideally. Yeah. Okay. Right. So this is the Fokker-Planck equation. Okay. D.
Is B the magnetic field?
Right. So the magnetic field is a function of time, of course. Yeah. But you see, so I will be doing. I will take the equation that we have and I will be trying to solve it. This Fokker-Planck equation, I will be trying to solve it. But the point is what I will. So by the time the medium is formed, the magnetic field has decayed. So heavy quark is produced much before the medium is formed, and by the time the medium is formed, the magnetic field has decayed. And what we will do is, to the linear order, we will ignore the magnetic field during the propagation, and the only effect of magnetic field goes into the initialization of the heavy quark spin. The initial polarization is governed by the magnetic field, and that's it. We forget the magnetic field, and we solve. So the time dependence is gone. I mean, it's anyway zero. So that's what we will be doing. But one can actually, then I will also show the results for next to leading order term, which has the time dependence as well. Okay. I'll parameterize it in some way. Okay, so this is the equation which one can, so the Fokker-Planck equation, which one can write if B is, the magnetic field is assumed to be independent of particle spin. So you can write it in this form. S is the spin, B tilde is the magnetic field times lambda in the heavy quark rest frame. And right, so P represents the probability to find the spin polarized particle in having an instantaneous orientation in this direction, theta and phi. Okay. Now, if we consider this spin space with the fixed radius, so the small s is fixed, and then we have theta and phi, then each point on the sphere represents a different spin orientation. And then we worry about how how does the probability depend on the spin orientation? Okay, and in this mu dot b, only theta plays a role, so there is no phi, because the angle between the spin axis and the magnetic axis is theta. Okay, so you see the phi dependence is all gone. Okay, in the equation, and basically now we are going to solve this. That 1 by d, we recognize that tau s as some time scale related to spin relaxation time. Okay, and then so this is the equation that we want to solve. Okay, the idea is that what we can do is we can solve it. So this equation can be written in the in this operator form, and the generic solution has this structure. It is just like finding the Green's function of the partial differential equation. Okay, and we just need to solve this, where the operator itself has time dependence. This L has time dependence through the magnetic field. Okay, so basically the magnetic field goes in H. H has time dependence, so this is time dependence. But what we will do is we'll assume that the magnetic field has just the time dependence. We ignore kind of the spatial X dependence, but just the time dependence we assume. Okay, and one can write it as a the operator takes this form alpha times another term which is time dependent term, and if we put in the values, alpha is quite small. Alpha, if you put in the values typical to heavy ion collision, the temperature and the magnetic field magnitude and so on, these numbers are quite small. It gives us enough reason to make a perturbative expansion in alpha. So this is the Dyson series that we obtained. So one can assume small perturbation and solve. And we can get we got the solution in terms of Legendre polynomials. Okay. But I don't show the solution here. What I show is the quantities which are sensitive to polarization. So average of cos theta and average of cos square theta. Okay, so this is the so-called vector polarization and the tensor polarization. Okay, for this is applicable for mesons and this is applicable for baryons. Okay, and as Bala, you were saying that where the time dependence goes. So there is one time dependence here, but the time dependence due to magnetic field is all put into in this term, the first term in alpha, and we assume the time, the decay of the magnetic field is parameterized in an exponential form. So with some time scale tau b, okay. So which is close enough, I would say, okay. So but nevertheless, you see, already we have some non-trivial term from the leading order, okay, and that comes from the fact that we have used the magnetic field to provide the initial condition for the spin. Yes, John.
At this point, the transverse momentum dependence, is that hidden in the what you call gamma V, the Lorentz gamma factor?
Right. It is in the gamma V. You don't see it here, but actually it will come in tau.
This is the correct
interpretation. This is the correct interpretation, yeah. There is no explicit momentum dependence here till now, but I will tell you how it comes in the okay. So, however, this is not how, so this is, all this is how the spin polarization takes place for a heavy quark, okay. But this is not how we measure polarization in the experiments. The way we measure polarization experiments is decay of particles and how the decay daughters make an anisotropy of decay daughters in the in some frame, some helicity frame or Collins-Hopper frame. So basically, theta star is the angle of one of the decay daughters. Let's say if the meson decays into two particles, then we choose one of them, and then that is the angle that it makes with respect to some axis defined appropriately. And so for baryons, this is the structure it takes, and for mesons, you have such kind of structure for decay distribution. Okay. So the idea is that if you don't have anisotropy in the decay distribution, then rho 0, is exactly equal to 1/3, and then you don't have any angular dependence. So basically, this angular dependence comes from the fact that in the rest frame of the particle, mother particle which decays, okay, the daughter particles are isotropic, okay, unless the mother particle itself is spin polarized, and therefore the decay daughters are emitted anisotropically. Very similar to, you imagine that there is in a very naive picture, suppose the rotating Earth splits up, then it will have more probability to throw the debris in that equatorial plane, something like that. Okay, so so what we can do is, using this distribution, we can write down this average of cos square theta and cos square theta star. Okay, and this polarization is defined as a deviation of rho 0 from 1/3. Okay, and in terms of the angle of the spin axis with the magnetic field, which is cos theta, which is theta, not theta star. Theta star is the emission of the daughter particle with respect to a quantization axis. Okay, so we had two leading order terms for heavy quark polarization is this, and one can show that that the ratios of average of cos theta star by cos theta and cos square theta star minus 1/3 by cos square theta minus 1/3 are constants, different constants, but are constants. Okay, and this is intuitive in the sense that if the heavy quark is not polarized, then the daughter particle will not be emitted anisotropically, and therefore you'll also have no polarization. So this polarization due to magnetic field of heavy quark. Okay, another thing that I should mention is that the polarization of the meson or baryon is completely, in our model, is completely attributed to the polarization of the heavy quark. The light quark the light quark polarization doesn't play a role, or in other words, the light quark which is associated with the meson comes from the medium, which we assume to be unpolarized. The medium is unpolarized. Okay, so okay, at least we know that at such high energies that we are considering, the medium is very less. The polarization is almost consistent with 0. Okay, from lambda polarization measurements. Okay. Yes.
Like, so at what point is this anisotropy in the heavy quark frame, and what point is it in the lab frame?
Right. So this is in the heavy quark frame.
This theta star is in the heavy quark frame.
And this is also in the heavy quark frame. Theta.
So everything is in the heavy quark.
In the heavy quark frame. And
so you have not come to
measure this. The experimentalists measure theta star. So I think since we are doing both in the heavy quark frame, the theory is consistent with how it is measured in the experiment. So the experimentalists give us this result, average of cos theta star and average of cos square theta star minus 1/3
They measure anisotropy in the Heavy-Quark frame.
in the Heavy-Quark frame. This is how the measurements are done. Choosing a quantization axis, the axis with which the angle theta star is measured, to be either the momentum axis, which is called the helicity frame, or some axis with something like some bisector of some angles, which is like the Collins operator. So they measure the polarization in the rest frame of the mother particle. That's right.
How do you like, you calculate the average momentum of the jet, is that, and then, I mean, you don't see the quarks, you don't see the Heavy-Quark.
Actually, no, you see, in experiments, you see the daughter particles.
Yes.
So
how do you go to the frame of the mother particle? You don't see the mother particle.
No, you don't see the mother particle, but I think correct me if I'm wrong. So I think the way it is done is, you know which two particles are kind of correlated, I guess, and then you know that these two particles must be coming from the decay of, and then you can simply boost back to the rest frame of the particle and look at the anisotropy of one of the daughter particles. I'm not very familiar with how this is done, but for sure, these numerators are measured in the rest frame of the mother particle, and therefore whatever we calculate is appropriate. So which we are doing in the Heavy-Quark S frame. So we don't really have to boost our observables to lab frame because the experiments also don't measure it in the lab frame. Right. So what we have is, so for example, this is for mesons. So there is this exponential decay with, and tau is the time in the time pass spent in the Heavy-Quark rest frame, and this tau s is the spin relaxation time, and tau, the amount of time that the Heavy-Quark spends in the medium can be simply calculated by putting some distance traveled r divided by the velocity. Okay, so this is Lorentz length contracted r by the transfer. So that is where the transverse momentum enters Jopo. So this is where my transverse momentum dependence goes. How much by naively calculating how much time the Heavy-Quark spends in the medium. Okay, tau. Right, and this is the result. So with all this, it's essentially two parameter fit, Cm and tau s. So one can. The idea is that so if I put all this back here, so with PT, you see PT will come in the denominator. Okay, so higher the PT, lower is the suppression of the polarization. So this qualitative picture is inbuilt in our formulation. Okay, the fact that there is increase with respect to the increase of polarization with respect to transverse momentum. Yes. So this we assume to be independent of PT. You are right. And one should be careful with that. Okay, but here this is an assumption that we because in other words, what one can do is one should actually calculate tau s from some microscopic calculation. Okay, and obtain it as a function of PT, and then you will have more appropriate parameterization with respect to PT. But in absence of that, we treat it as a single parameter.
Yeah, but why I was telling that if the PT is different, like you're probing a microscopic system with different scale. So tau s should probably be dependent on that PT, no?
Sure, but one thing is, this is in the Heavy-Quark rest frame. Okay, so somehow I don't expect, so all this is happening in the Heavy-Quark rest frame. So I don't expect, you wouldn't expect that the momentum of the Heavy-Quark plays a role in spin relaxation, yeah?
Right, I mean, you're telling that all the corrections which we are anticipating should be PT by Heavy-Quark mass whole square or something like that.
Yeah, no, not even that. What I'm saying is tau s is the spin, is a microscopic property, the spin relaxation time. And tau is a macroscopic scale, how much time it takes to cross the medium essentially, escape the medium, okay. So PT goes in tau because, then what is the length that the Heavy-Quark sees to the boundary of the fireball, that is Lorentz contracted, and then by the velocity.
Yeah, so in this limiting case, there are no mixing between the long distance and short distance dynamics, roughly.
Okay, well, there is tau, I mean, The microscopic scale is, sorry? Yeah, well, I mean, tau s is the spin relaxation time. So the microscopic picture, microscopic information is all here. And yeah. So,
If the mass of the quark is known, then the spin will be
If the mass of the quark is low, suppose for you are showing for heavy quarks, if one does the same calculation for U and D, then will he find that the U and D quarks will
we
get
cannot do it for-
unpolarized more quickly? If the mass is smaller, then
we cannot do it for U and D quarks.
yeah, obviously. But you are saying that you are considering U D quarks are unpolarized.
So this is like, the theory of pollen grains in air. So the pollen grains gets kicked by the medium particle. They have this small angular momentum transfer dynamics. Here we are considering this small angular momentum transfer dynamics for heavy particles. So the idea is very similar to what we do for Brownian motion, but in the angular momentum space. So we cannot, in that sense, we cannot have. So there has to be a separation of scales. So for the medium particle and the heavy particle.
No, I mean when the heavy quark is combining with some other quark, U or D, and you are detecting that, then does the U and D quark spin contribute to the final detected particle?
So in what I show here, no, because once I start taking this to be a constant, I'm implicitly assuming that the polarization of the heavy hadrons is completely due to heavy quark. Okay.
Under what condition will that be true?
So the idea is that any spin flip processes will be less likely for heavy quarks compared to the light quark spin flip. So
that related to some inertia or mass, is that?
Yeah, one can in that sense
okay,
consider that in that way. Okay. Right. So yeah. So basically the idea is that the qualitative picture is very simple, and that is there is this qualitative physics that we have. It's just that the fact that why we get this increase is completely explained by the Brownian motion in angular momentum space. Okay. And now let's look at another observable. So I said that that there is this QGP through which heavy quark propagates, and then the longer it stays in the medium, the more depolarized it is. So high PT particles are more polarized and low PT particles are less polarized, and that was observed, explained. But QGP is not a spherical fireball. You have this asymmetric QGP. Okay. So this provides us, so you have an ensemble of heavy quarks which is spin polarized at the very early time, and then it propagates to the asymmetric QGP. So for example, for same PT, if the heavy quark is moving along y direction, then it has longer path length to travel, and therefore it is more depolarized, less polarized compared to x direction. Okay. So one can systematically define this so-called polarization harmonics, like flow harmonics. Okay. And then we can go ahead and try to do that. So remember this this R that we had here. Okay, so I said that the average radius of the fireball is R that the heavy quark traverses, but this need not be a fixed parameter. That's what. So this is how do we define that? So how do we relate with that? So the idea is that consider the average path length along a direction phi. So along all the heavy quarks moving along a phi direction, let's say it traverses a average path length L phi, which we can parameterize in. So we can just do a Fourier series expansion. Okay, and we assume the geometry of the fireball, this deformation of the boundary. Okay, the radius to be also have this kind of Taylor expansion, and under the approximation that you have convex geometries with weak anisotropy. So this deformation is not too much. If you have small deformations, then so there are these theorems in geometry, in this integral geometry, which say that for convex geometries with weak anisotropies, this fractional deformations are for the average path length traversed along L along a phi direction, and the average deformation ratio of the relative deformation are equal, and this leads to the relation between ln and an. Also, in initial state, we can define the eccentricities that you can obtain from Glauber model. So eccentricities are defined like this, okay, weighted average with R. So we can put this R here and calculate the eccentricities. So eccentricities can be modeled from obtained from models. So the point is, one can infer the information about the average path length traveled and the eccentricities calculated with a minus sign. This is actually very important. All this says is that the average path length along, so if eccentricity is positive, so then the average there is a so it tells you whether it's oblate or prolate shape. Okay, so depending on that, you have the average path length traversed. Okay, and we had this solution for Fokker-Planck equation that I already showed. So in terms of polarization of baryons and mesons. So in general, you have this spin polarization alignment, some A constant times either alpha minus alpha. Alpha is 6 or 2, whether it's baryon or meson. Okay, and so this is the general form that we have.
The potential form that you have, these expressions.
Right.
These are assuming that the magnetic field has instantaneously
Right. So it's the
exponentially.
same heavy quarks now. Yeah.
But now you're talking about a medium. So
Right.
then-
So the heavy quarks, even in the previous picture that I had, even in this picture, the heavy quarks which were polarized along the magnetic field, it got depolarized by traversing through the medium. Okay, so there's this medium formed. Okay, now the only thing is this medium is not isotropic. Okay, so can we take this path length dependence polarization and define harmonics? So the medium is in general anisotropic. So I'm just trying to define the way in which direction the heavy quark traverses. It may traverse a longer distance or a shorter distance.
But when you're discussing about traversing through the medium,
Yes.
then the magnetic field will
gone.
not decay by this.
No, magnetic field is gone.
Why?
Magnetic field
Because
is
if you have a conductivity, then the magnetic field will
okay.
stay in the
So
medium.
that's an approx. So the idea is okay. So one should be able to then one should take the next two leading order terms and put this also. But these are corrections because as I showed that alpha, the strength of the magnetic field is it depends on the strength of the magnetic. These are initial magnetic fields. Even if I put in the maximum possible value of alpha is actually very small. For charm, this is few percent and even less for bottom. Okay, we are dealing with charm, but still we can make a perturbative treatment. So in principle, that should be taken into account, but that is a correction. So I'm ignoring that just for making things simple analytically.
Because you're coming to low PT particles now. That's why I'm a little bit worried because these effects will be becoming important. For high
Yes,
PT, of
yes.
course, it doesn't matter.
Right. Yes, you're right. Right. So this is a general form of the polarization or spin alignment, okay, that we have. And then the idea is that the tau, the time spent in the medium, will now depend on the average path length along phi. Okay. So what one can do is one can simply take this tau, plug it here, okay, and do Taylor expansion in small epsilons. Assuming small deformations, so small anisotropies, you can do this standard expansion that we do. Okay, we can do a Taylor expansion. So the first term is what exactly we obtained in the previous work. This is the first term, and then these are the polarization harmonics that we define. Okay, which depends on the initial eccentricity. So if I were to make an analogy with momentum observables, then this would be the polarization spectrum, the PT spectrum of polarization, and these are the polarization harmonics. This would be the exact analogy. Okay, and then of course this is just the this is just the polarization function that we have. I mean, if I were to have the full spectrum, then I should multiply it with the momentum spectrum as well. So if I were to have fully differential polarization, then this should be convoluted with the momentum distribution as well. So so first of all, I just show here P2, which is the second polarization harmonics, so-called elliptic polarization. We cannot say that elliptic polarization is a term which is already taken, yeah, because we study about elliptic polarization, circular polarization in textbooks. So this is like elliptic polarization harmonics. The second polarization harmonics as a function of PT, it decreases, okay, which is also very intuitive because the high PT particles are fast and they kind of escape without getting depolarized, and therefore they're not sensitive to the shape of the medium. Whereas the low PT ones, which spend some time, are sensitive to the shape, and then you see that there is a sizable polarization harmonic. Okay.
How do you determine this tau s?
Tau s is a parameter. So tau s is something. So we do not calculate it. We fitted tau s from the previous data for this for this one. So tau s is fitted, and we have a number tau s. So that is what we use for this year. I put tau s to be a number. L0 is the same value which we put for R in the previous. So we use the same numbers that we had to explain the data, and we get second polarization harmonics as shown here. Okay, and then what I can do is I can integrate with the momentum and obtain the averaged polarization harmonics as well. This average P2, like V2, we have average P2, and so for that what we do is we use some parameterized form of prompt momentum spectrum. Okay, and the number is actually quite significant. This average P2 is 0.17. You should compare this with average V2, which is of the order of few percent. This is like 17%, or at least of the order of 10%. So this is something which is a measurable quantity, I would say, and this needs an immediate measurement because since the spectrum, the so-called polarization spectrum, is already measured, this flow or harmonics would not be such a difficult measurement, at least for D star plus meson. Okay. So I have been working on this with my student Saurav, and we have made some further progress, and we're actually working on many different. So for example, all these models that I have explained to you is very simplistic. Is the minimal model that I have. So static constant temperature fireballs we have assumed. So one has to have this more realistic space-time evolution. There is this, one has to, so whatever PT I show the data to you should be dragged. Actually, there should be momentum drag and diffusion, which one should also take into account in the whole calculation. Okay, and one should have this linear response for spin, diffusion, and drag. Obtain Kubo relations for that, and calculate tau s for heavy quarks. We also need to have this derivation for Einstein-Stokes like relation between spin, diffusion, and drag. So that is something which one should do as a theoretical, whether it is D equal to lambda T or something else. I mean, there are some factors there. So that can be followed up from derivation of rotational Fokker-Planck equation from kinetic theory using non-local collision terms. Okay, so this is essentially a new. I think it's a new area to study non-equilibrium. This is non-equilibrium spin. This is not equilibrium. This is not spin hydrodynamics. This is out of equilibrium spin dynamics. Yeah, this is something new in heavy ion collision. Okay, so any questions still here? Because now I took this. I will take some extra time to explain something different. Any questions?
Actually.
Yes.
So before the medium, you things has two parts, right? Before QGP and after QGP.
Right.
In this. So before QGP, you explained every polarization, everything in the form of just one parameter, just theta, right? There is no phi dependence there. Why? But after QGP, there is pi dependence and theta dependence.
There is never phi. Okay, so maybe we have to. Okay, let me explain there are the various phis which I've introduced. So let me tell you what. So theta is the direction of spin with respect to magnetic field. Okay, so that goes into the Hamiltonian. Hamiltonian doesn't depend on phi. Okay, so only theta comes here, and therefore the Fokker-Planck equation is sensitive only to theta. There is no, so the angle that the spin makes with magnetic field. Okay, so that is, and the phi that you saw.
No, to that slide there is
Here, this phi.
Here itself you say that theta, phi, everything is there, right?
Yeah, it's all there. But the idea is that the Fokker-Planck equation doesn't tell you the phi evolution. It only tells you how theta changes. So it can precess around magnetic field, but what is this change with respect to the magnetic field? That is what is governed by the Fokker-Planck equation. Okay, that is one thing. The phi this doesn't care.
Okay, and then another question. You said the particles will become isotropic if the parent is something. What is that?
So if the mother nuclei, mother particle is not polarized, okay, then there is, then it, if the because so what happens is that you can have spin of the, so for example, let's say D star meson, okay, spin 1 vector meson, okay. So there is so because it's spin 1 particle, of course, if you take only one particle, then you can see that there is some angle that the daughter particles makes with the spin axis. Whatever you can define for the way it is defined is not so easy, but yeah, but some anisotropy you will observe. But the fact is, on an average, this average of cos square theta becomes exactly 1/3 if there is no special alignment of spin for the mesons. Okay, so if there are no spin alignment, then average of cos square theta becomes 1/3. Okay, so deviation from 1/3 of cos square theta, average cos square theta, is what we say, what we attribute to spin alignment of mesons. Okay, so this is what this is. This quantity is delta rho 0 0 is deviation of rho 0 from 1/3. Okay, so that's how it is defined. So there's this spin density matrix that you obtain, and you can define this. Okay, so that's what it is.
One question I will talk outside, but so you showed that P2 versus PT.
Yes.
Yeah.
Yes.
So this one in the medium you calculate.
Okay, so right.
So,
yeah.
So the question is, if I ask, can you calculate that just the PT dependence, just the vacuum, nothing and
Vacuum?
Yeah.
No, but if there is no medium, then there is no
Let's say,
depolarization.
let's say initial magnetic moment, magnetic field is there, and they suffer no medium effect.
So the idea is, you see, if you have initial magnetic moment, magnetic alignment, initial spin alignment due to magnetic field, okay, then, and if there is no medium, then whatever you have initially, it just stays.
But as a function of PT, how it will be?
So then you will
the constant always?
Yeah, there won't be any variation. It will be some fixed number. Right? There won't be any, because there is no medium boundary to cross. So the idea is that the longer time it spends in the medium, there is more interaction with the medium constitutes, more depolarized it gets. But if there is no medium, no such thing happens. Okay. So
no, the two things. One is the magnetic field is dropping.
That is, so magnetic field, I don't
so,
even consider. It's dropped. It's gone to 0. Okay. So I don't even consider that anymore. So because I'm making a perturbative treatment. Okay. Okay. So let's move on to, so these are the signals of magnetic field that I explained to you. Now. So this is very strong magnetic field and very clean signals that I try to convince that we can get from polarization. But we can actually apply it to study something very, very interesting. This is something which I'm very proud of, recently what I did. So tau leptons in heavy ion collision. Since the tau leptons are very special leptons, they decay. So leptons, for example, and they decay with some time scale, which is more than the fireball lifetime. So it decays outside the fireball, okay. And the mass is of the order of some mass. So it is also supposed to be produced at least in early stages of the fireball when the initial binary collisions are I mean, hard scatterings will produce, soft scatterings will not make these large mass particles, leptons. They are leptons, so they are not color charged. So if they are produced and then they experience the magnetic field and then the spin is aligned, they go out, they decay. Okay, then we can look at the decay daughters and we can try to understand. So in decay of tau, whether tau plus and tau minus decays identically. Polarized tau plus and tau minus, if they do not decay identically, okay, then there is a CP violation signal that we can try to look into it. Okay. However, tau decays via weak interaction, and therefore there are neutrinos in the final state. So in heavy ion collision, neutrinos being in the final state, this is too much of background, and we cannot study tau decay in heavy ion collision. But we have EPCs. So we have ultra peripheral collision, which is a very, very clean environment. You just produce via photon fusion. You produce two tau pairs, essentially, tau plus, tau minus, okay. And then this tau plus, tau minus decays clean environment. This, by the way, I must tell you that these processes have been measured by CMS and Atlas, and to find anomalous magnetic moment of tau in UPCs. Okay, so there are measurements. There are data for like of the order of 100 taus. Okay, so so the idea is the following. Okay, we consider the tau leptons produced in UPCs. Okay, and where the magnetic field is, so UPCs will be having this kind of impact parameter. So magnetic field is still quite sizable. You know, it's very strong magnetic field. Rather, I would tell you that this photon processes are because of the strong electromagnetic field itself. Okay, so they must be already, and since we can produce taus, so this must be very strong photons. I mean, the field is quite strong, I would say. Okay, so what we do is, so what I propose is the following. So in this tau plus tau minus, okay, I look at the anisotropy of the decay daughters and try to quantify this asymmetry between tau plus and tau minus, and whether I can find a CP odd sensitive observable. Okay, so this is something. So let's look at again. We go back to the rest frame of the tau. Okay, and define tau polarization vector aligned along the magnetic field. So the idea is that the tau is polarized in its rest frame along the magnetic field that it experiences in its own rest frame. The tau spin gets polarized. It's very similar to what we did for Heavy-Quark. Okay, and in this framework but there is no medium here. So this is just UPCs, tau being produced, and then the decay. Okay, no medium. So we adopt helicity frame formalism. Okay, so the helicity polarization is along, the polarization along the velocity of the particle. So we can actually write down in terms of the angle psi that the velocity and the polarization makes. Okay, so polarization is along magnetic field. So psi is the angle between the velocity of the tau and the magnetic field direction in the rest of the particle. Okay, and now what we can do is we can average. So this is cos psi. So now if we consider this and we average over full psi range of emission angle, okay, then we get it to be zero. The helicity polarization becomes zero, and then we don't have any signal to compare. Okay, so what I propose is average over half ensemble. Half ensemble is the following. So what I do is, or what we propose is that we take half of so psi is the angle with respect to the magnetic field. Okay, so we define psi for tau plus and tau minus. Okay, so we only take half of the range of psi for tau plus, and then the other half for tau minus, the complementary angles. And so for example, magnetic field is in this direction, so we'll only take all the tau plus in the pointing towards the magnetic field, then all the tau minus pointing towards the opposite to the magnetic field. Okay, and average over the first half and the second half. Okay, so that leaves some magnitude to be explored. Okay, so this is the expression in the helicity frame. Okay, and then and in the most general case we have p tau plus minus, which is alpha is the electromagnetic factor. Okay, so that simply cancels in the ratio of which we are going to define here, and the ratio of p tau plus the polarization of tau plus and tau minus, okay, is what we want to obtain, but with this half ensemble average. Okay, so in terms of so first of all we will be working in collinear approximation where the decay of, so for example the tau decays in a pion and a neutrino. Okay, so the angle theta pi is in terms of the momentum fraction, and so energy of pi by energy of tau is what we can write. Okay, and in terms of half ensemble, so this average is pi. So for tau minus, it's average over all pi minus on one half. Then the other one is on the other half. However, since alpha is the electromagnetic factor, we don't expect any CP odd term there. It's only in the weak decay that we are trying to find. So alpha is the same for all. So in the ratio of p tau plus by p tau minus, we only get this term, these two terms, where the averages are defined over half, complementary halves of the ensemble. Okay, and we propose that this delta pi is deviation from 0. It should be ideally 1. If there is no CP violation, there should be 1. So deviation from 0 is signal of CP violation in tau. So this essentially is using the magnetic field to polarize the tau leptons and then study the relative anisotropy or relative polarization of the tau plus and tau minus. And if they don't decay identically, so tau plus which is polarized along the magnetic field and tau minus which is polarized opposite to the magnetic field should be CP symmetric. Yeah, that decay should be exactly equal to 1, that polarization. So deviation from 1 is what we propose to be a polarization observable. So this we can do for, so this we can play the same game for different decay channels, okay, for in the leptonic decay and the vector meson decay sectors as well, okay. And okay, so what are the caveats? So I talked about all this, but the point here is the following. There are several caveats, of course. First of all, in UPCs, how do we know the direction of the impact parameter and therefore the direction of the magnetic field? Okay, so that is already very number 1. Number 2, how do we know the energy of the tau that is being that is coming in? Yeah, so we measure the pion energy, but tau we don't know. Tau has decayed. So how do we know these things? So this proposal heavily depends on 0-degree calorimeter. Okay, so the idea is that we start with some energy of heavy ions, colliding heavy ions. Okay, and then they don't essentially collide; they simply deflect because of the ultra peripheral collisions, and they leave some energy, deposit some energy in the 0-degree calorimeter. So the difference of the colliding energy and the ones deposited in the 0-degree calorimeter will give you the energy of tau. That is 1, and the deflection direction will give you the direction of deflection. Okay, that will tell you what is the impact parameter direction, and therefore the magnetic field direction is perpendicular to. So basically, the deflection in the 0-degree calorimeter on one end and the other end, you can draw a plane, and perpendicular that will be magnetic field. Okay, so combining all this, so basically this proposal depends heavily on upgradation of 0-degree calorimeter. Okay, so but there is huge physics, trade-off in the sense that it opens up UPCs as the arena for BSM physics. Okay, so and this is not the first time that we are trying to propose polarized tau decay as CP violation, because polarized tau decays have been proposed in polarized electron-positron collisions. So there have been some proposals where electron-positron beams are polarized so that they produce polarized, but it's difficult to produce polarized electron-positron beams to get polarized tau and then study its decay. But this one is a natural place where whatever taus are produced in UPCs are by definition polarized along the magnetic field. So yeah, so this, so of course there is more data to be. One has to actually have a lot of data. So so for example, recent CMS and Atlas in UPCs have only hundreds of the order of 100 taus observed. Okay, so but I guess polarization observation requires much more statistics than that. Okay, and yeah, but there are upgrades planned, and then there is high luminosity LHC coming up. So yeah, my point is that this could be one of the interesting physics could be studied in UPCs. If UPCs are people are going to keep taking data for UPCs. Thank you.
Thank you, Amaresh, for this insightful magnetic field and polarization. Yeah. So any question?
Curiosity, because I'm not extremely familiar with this. I mean, what is a typical time scale in the magnetic field that are produced in heavy ion to make a spin flip or to align the spin of a heavy quark to the magnetic field? How much time does it take?
Right. So this is okay. At least I have in this sense, I must admit that I have not attributed any time scale to that. So I have assumed that the taus are or all the particles that are so heavy quarks are aligned along the magnetic field direction, but
you showed, I mean, if I remember correctly, the magnetic field dropped by a factor 2.
Yes.
During a time scale which is half a Fermi.
Right.
Okay. So no, my question is simple. I mean, what is the Larmor frequency? I mean, that you should be able to estimate. And
One should be
I'm
able to
just curious to know the number. That's all.
Yeah.
Okay.
I think, yeah, this I have not tried, but I can let you know. I mean, this is simple calculation. Yeah.
Yeah, it also depends on the time expanding system.
No, it will not depend on the system actually. It will only depend on properties of the heavy quark and the magnetic field magnitude itself. So it should not depend on the system at all. But this is a simple calculation to be done. I think, yeah, I should be able to maybe have something for you by the.
The gyromagnetic factor is down by the mass of the heavy quark, so that's small. I mean, the relation between spin and magnetic moment, and
Right.
and this is magnetic moment is what drives this time scale.
Yes. No, it will not depend on the medium. So how the heavy quark spin align in the magnetic field will. Yeah, I mean, okay, so if the time scale is
So that calculation is not
larger
yet.
than the magnetic field decay time, then it will come into play. You are right. Yeah.
So it's a interesting talk, I would say. And the proposal I mean, kind of putting to measure this, what I can say, this tau, what you say about the tau. So the assumptions of taking that, I mean, the energy, and from the 0-degree calorimeter, the energy, but how would you sure that the energy which is missing is basically the tau energy?
No,
first
but
of all?
actually, okay. Okay, I mean, if I were to, okay, you're asking that if this is, so I'm a theorist. I would just assume that if this is the process that takes place in UPCs here, then the missing energy which is not deposited in 0-degree calorimeter is just taken by the 2 taus. So I mean, for the most ideal UPC, where I observe 2 taus, okay, I will assume that everything goes to tau. So there is energy of the colliding beams and the energy deposited in the 0-degree calorimeter. Unless there is due to some fragmentation, some part is lost, I would assume that this difference is what is tau energy.
If I assume that this is the case, and another thing is you take the half ensemble average.
Half
So
ensemble average, yeah.
first of all, in UPCs, so the number of taus is produced very less.
Right, I
And
agree. So
then
this is
again-
you need statistics.
And then
for this.
again, you take the half ensemble.
Right.
I mean,
Yeah, so the statistics has to be improved. So one has to, of course, go to this. I don't know. I mean, so after I think okay. The statistics need to be drastically improved. You are right there. So that I already I gave a disclaimer that statistics has to be improved, and the 0-degree calorimeter has to also be improved.
Yeah, it needs some systematic experimental thinking. how to
Yeah,
set
so
up.
this is one has to really do something for making this observably significant.
thank you, thank you.
Any further question? No? Okay, let's thank.